Okay, in this section we're going to talk about solving some exponential and log equations. So I'll give you some of the most common equations that I usually teach in my classes. The first thing I want to talk about is sometimes you don't really need any fancy tricks to solve exponential equations. Like for instance here I have 5 to the 2x plus 1 equals 1/25. Well, 1/25 can be written as 1 over 5 squared, and then 1 over 5 squared can be written as 5 to the negative 2. So since I have the same base on each side, 5 to the 2x plus 1 equals 5 to the negative 2. Since these two bases are equal, then the two exponents must be equal for this equation to be true. So I can just set 2x plus 1 equal to negative 2, and you guys know how to solve that from there. Just subtract 1, then divide by 2, and you get x equal to negative 3/2. Another example here is 27 to the x squared equals 9 to the x. Well, I can actually write 27 as 3 to a power, and I can write 9 as 3 to a power. 27 is 3 to the third power, and 9 is 3 to the second power. And then using my exponent properties, 3 to the third power raised to the x squared, I just multiply the exponents and I get 3 to the 3x squared. Same thing here, multiply the exponents and I get 3 to the 2x. And then now that I've got the same base on both sides, I have 3 to the 3x squared equals 3 to the 2x. Then 3 to the x squared, 3 times x squared must equal 2x. And so then I can just solve this using algebra that I've learned before. Let's subtract 2x from both sides, and I get 3x squared minus 2x equals 0. Let's factor x out of the left-hand side, so I get x times 3x minus 2 equals 0. So I know that the only solution to this is if x equals 0 or 3x minus 2 equals 0. So x equals 0 is one solution, and then if you solve this equation, x equal 2/3 is the other solution. So, if that's the case, then you can, solve it without using logs. But in many cases, we'll have problems where we can't equate the bases. Like here we have 7 to the 2n equals 325. Well, there's no way that I can write 7 and 325 using the same base. So what I'm going to do in order to get this exponent as a factor, I'm going to just take the log of both sides. Now you can use the common log or the natural log here, but I'm going to use the common log. So remember, if m equals n, then the log of m must equal the log of n. That's one of our properties. And now I can write this using the log property, log of 7 to the 2n as 2n times the log of 7. Now I'm going to go ahead and write this a different way. You may or may not need to put in this step, but this is actually 2 times the log of 7 times n. And the log of 7, 2 times the log of 7 is just a number. So if I want to isolate n, I can just divide both sides by this number. So if I divide the left side by 2 log 7, then it'll just cancel and I'll get n on the left. And then if I divide the right by 2 log of 7, I just get log of 325 divided by 2 log of 7. And make sure you put that in parentheses so that when you put it in the calculator, you get the right answer. 1.486. Now, here's another one, and I'll leave you to read this one, but you can pause the video if you need to. But notice here on this one, first thing I did is I divided both sides by 10, and then I took the log of both sides. Now, here I used the natural log on both sides. And on both of these problems, it doesn't really matter which one you use, as long as you use the same log on each side of the equal sign. Okay, this one, when you have unknown exponents on both sides, that makes the problem quite a bit more difficult. So here I have 3 to the 2x minus 1 equals 7 to the 3x plus 2. So what I'm going to do is I'm going to take the natural log of both sides, and then using my log property, I can write this as 2x minus 1 times natural log of 3. and I can write this as 3x plus 2 times natural log of 7. And then when I distribute, I'm going to get 2x times natural log of 3 here, right here, and then minus 1 times natural log of 3 here. And then over here when I distribute, I get 3x times natural log of 7 here, and then 2 times natural log of 7 here. Okay, now if you'll notice, this has an x in it, and this has an x in it. So I want those two terms on the same side of the equal sign. So let's move this term to the left, and so I have 2x natural log of 3 minus 3x natural log of 7. And I want the minus natural log of 3 on the other side since it doesn't have an x in it. So I'll add it to both sides, and on the right hand side I'll get 2 natural log of 7 plus natural log of 3. Well, now I can factor the x out of these two terms, and I get x times 2 natural log of 3 minus 3 times natural log of 7, and then equals what I had on the right side. Then if I divide both sides by this expression, then that will isolate the x, and so I'll get x equals what I have on the right side, 2 natural log of 7 plus natural log of 3, divided by 2 natural log of 3 minus 3 natural log of 7. Now when you do this on the calculator, make sure you put parentheses around the numerator and parentheses around the denominator so that it'll do the calculation correctly. Okay? Alright, now if I said a while ago it doesn't matter whether you do natural log or common log, and it really doesn't matter in this case, but generally if you have a base e in your exponential equation, it usually works better if you take the natural log. Because when you take the natural log of both sides, well, the natural log of e to a power, using one of the properties we talked about earlier, the natural log of e to a power is just the power. So the natural log of e to the 5x minus 2 would just be 5x minus 2. So this would be on the left 5x minus 2, on the right you'd have a natural log of 25. And then you could just solve that. You could add 2 to both sides and then divide by 5 to get the answer. If your base is base 10, then you want to use the common log, because if you take the common log of 10 to a power, you just get the power. So in this example, I'd have the power 1 minus c equals the log of 20, and then I can solve that, subtract 1 from both sides, then divide by negative 1. So if I subtract 1, I get minus c equals the log of 20 minus 1. But then if I multiply or divide both sides by negative 1, you get c equals 1 minus the log of 20, which is this. Okay. Now, I'm going to show you a couple more equations. Now, we're going to talk about log equations. Now, log equations generally come in two forms. One form is you can get a log equal to a number. Now you might have to do some log properties first, but like right here I have the log of 2x minus the log of x minus 3, and these have the same base, base 10. Well, and then I have it equal 1. Well, I can actually combine these logs into a single log using my log property. Remember, the log of m minus the log of n can be written as the log of m, which is 2x, over the log of n, which is x minus 3. So I can write that as this as a single log, and then over here I have 1. Well, I can convert this to exponential form now, because remember there's an understood base of 10 here. So that would be 10 to the first power equals the argument, this. Now once I get here, now I can just solve it using the algebra that I've learned in the past. So I can multiply both sides by x minus 3 to get rid of the denominator. So I get 10 times x minus 3 equals 2x. And then distribute here 10x minus 30 equals 2x. Then subtract 2x from both sides, add 30 to both sides, and I get 8x equals 30. Then divide by 8, and I get 15/4, or 3.75. Now what you want to do though is make sure that 3.75 is in the domain of your expression. So can I take the log of 2 times 3.75? Well, since 2 times 3.75 is positive, I can. What about x minus 3? What about 3.75 minus 3? Okay, well 3.75 minus 3, that's a positive number, so I'm okay there. So mainly I'm just checking to make sure that I don't get an answer that's going to give me a negative or 0 when I take the log. Okay, another thing that can happen is maybe you have a log on both sides. Well, if you have a log on both sides, you can use the one-to-one property and just throw away the logs. So here I have the natural log of 3z plus 8, and over here I have the natural log of 2z plus 2 plus the natural log of z minus 2. So the first thing I'm going to do is I'm going to combine these logs into a single log. Remember, the natural log of this plus the natural log of this is the natural log of this times this. So it's going to be the natural log of 2z plus 2 times z minus 2. Okay, well now I have a log on the left equal to a log on the right. So if I have a single log on both sides, I can just drop the logs. So I'm going to drop the logs and just get 3z plus 8 equals the product of 2z plus 2 times z minus 2. Now all I have is just a quadratic equation to solve. So I solve this, I FOIL this, and I get 2z squared minus 2z minus 4. Then I subtract the 3z and the 8 across, and I get 2z squared minus 5z minus 12 equals 0. Then I can solve this by factoring, so I get 2z plus 3 times z minus 4 equals 0. So 2z plus 3 equals 0, or z minus 4 equals 0, which means z equals negative 3 halves, or z equals 4. Now, the negative 3 halves will not work. The only answer is z equals 4. If you go back up here and plug negative 3 halves into each of these logs, you'll find that at least one of them will give you a negative for the argument. So that's why the negative 3 halves does not work. Okay, let's do a couple more. This one has log of the x cubed, where the argument is cubed, and then this one is the log of x. So this is the entire log squared. So on this one, we can write this one as 3 times log of x. But we can't do a property. There's no property for this one because the 2 is on the outside of the log. But what we can do is we subtract this term from both sides. We can move this term to the other side. It becomes minus, and that'll give us this equation. And then I can factor a log out of this. So if I factor a log out of this, I get log of x equals log of x minus 3. Well, now I know that log of x must equal 0, or log of x minus 3 equals 0. Well, since I know log of x equals 0, I can solve this by just putting in exponential form. Remember, the base is 10. So 10 to the 0 would equal x, or x is 1. If I solve this one, I get log of x equals 3, and again I know the base is 10. So exponential form for this would be 10 to the third power equals x, and 10 to the third power is 1,000. So your two answers there are x equal 1, x equal 1,000. Part D here, I can simplify this. Remember, you can take this 4 and put it back up here as an exponent. You can take this 1/2 and you can put it back up here as an exponent. And you can take this 1/3 and put it back up here as an exponent for 8. So that would be log of 2 to the 4th, log of 4 to the 1/2 equals 2 minus log of 8 to the 1/3. And of course, what we're trying to solve for is the base x. So now, this would be log of 16 base x. This would be 4 to the 1/2 would be log of 2 base x. And then log of 8 to the 1/3 would be log of 2 base x. Well, if you'll notice here, I have minus log of 2 on the left, and I have minus log of 2 on the right, so they just cancel, and I get log of 16 base 2. Well, if I have log of 16 base x equal 2. So that would mean that x to the second power equals 16. So x would have to be plus or minus 4. But we know the base cannot be negative, so the only answer that makes sense is for the base to be x equal 4. Okay. And then there's one more problem down here, and this one can be a little tricky. But really on this one, when you say 10 to the common log of 2a minus 7, well, that's just 2a minus 7. So really, that equation is just simply solving 2a minus 7 equal 8. And then when you solve that, you get a equals 15 halves. Okay, so that ends the section on solving log and exponential equations. In the next section, we'll look at some applications.